Hello, my name is Anurag. Welcome to session number 5 in the series Digital Circuit Design using VHDL. And in this in this session, I am going to talk about some of the coding constructs in VHDL that are going to assist you to progress further in the journey to learn doing VLSI. So let's get started. So you fire Vivado and then you create a project, right? So we have created the project earlier also, right? So it's going to be the same stuff. I'll call this project as uh, combinational circuits, correct? And I'm going to say next, and this is a RTL project. Next, and I'm not going to add any sources, but I'm going to make sure that the target language is VHDL and the simulator language is mixed. Next, I'm also not going to add any constraints, right? So here I'm going to choose a device from general purpose. Family is RTX 7. Package is CSG 324 pins. And then speed grade is -1. And then the last one is the one which I have. And I'm going to say finish. So what's the broad agenda? I have to show you that in VHDL there are something called primary design units, secondary design units. Primary design units is an entity, and a secondary design unit is architecture. So entity is basically an outline of a circuit. It's basically an idea of ports which are going to be input ports, output ports, or in out ports, right? So the entity is basically a outline of a design. Now entity can also be used to pass certain information to the component which is instantiated, right? So that so that we can basically scale the design, right? Mostly it's used for scaling of the design or fixing some constraints, right? So that entity basically can have multiple architectures, and the the architecture will be which will be paired with the entity during instantiation of a component, that that is decided by the script called configuration, right? So we have an entity architecture pair representing a component which is instantiated, and it is guided by configuration in case there are more than one architectures. Then we can put all the components, okay, in a package, right, which belongs to a certain library. Now as I have told you example, so for example, let's say you go to a library and you want to check out a book, and the book is going to be in fluid dynamics, right, in mechanical engineering. So I might go to the library, go to a row which is for mechanical engineering, then go to a particular rack where there are books on fluid dynamics. So library, package, and component is something like that, right? So we will see how to create a package and how to populate a package with components. Then there is something called package body. Now in package itself is sufficient for most of the designs, but in case the package has got function declarations or procedure declaration, then its body is specified in the package body, right? Similarly, if there are constants which are declared in package but they are not assigned, they are referred to as deferred constants, and these constants are going to be specified in the package body. So now you can see that there is a pair, right? Entity pairs with architecture. Entity is a primary design unit. It can stand on its own. Entity need not have architecture also, but then entity without architecture is non-functional, right? Now architecture is a secondary design unit. It depends on entity to exist before its existence, right? So if there is no entity, then architecture is not valid. So that's why it is called a secondary design unit. Similarly, a package has to be there for a package body to exist. So package is a primary design unit and package body is a secondary design unit, right? So all these things are there in a library. So every project, when I create a project, it has its own library, right? That's by default there. Then there is another library which is implicitly visible, that is called a standard library. Okay, so some of the things which are there in standard libraries can be used, but then there is a library called IEEE, uh, and then there is a package called std underscore logic underscore 1164, right? So this basically has to be specified, okay, at the top of your code, so that that's included in your design, right? So there are three kinds of libraries. One is which is your local library to a project. Second is the work library, which basically, sorry, the standard library, which is by default visible to your project, you don't have to specify. And then a IEEE library, which you have to specify at the top of the code. So we are going to look at, with examples, we are going to look at these design units, right? And then we will create a component and then place it in a package in a library, right? And then we will see how to instantiate a component from this declaration. So let's go ahead. This is a blank project, and let me just, okay, so this is a flow navigator here, and we have seen earlier what is a flow navigator. Now what I'm going to do is, under sources, I'm going to right click and say add sources, and then create a design source. Next, I'm going to create a file, and the file name should be same as the entity name. It's not compulsory, but it will help you debug, right? So if there are errors in a hierarchical design, it will point to entity name, not the file name. Now the file name, if it is same as the entity name, it will be easy for you to trace the file where you have done the error. Okay, so let's go ahead and declare. So let's say I'm going to do a half header. Okay, so this is a half header, and I am going to define my own library here. So all I have to do is just type it. So I'm going to say my circuits. Okay, so my circuits is the library, and it's local to the project, and say finish. As soon as I do that, it says, okay, let's do the architecture now. You have done the entity called half header. Let's say architecture is called HA, short form for half header, and I'll tell you that you can even use the same name, right? Or you can skip this and you can write your own entity. So let's see. A half header has got two inputs. These are the scalar inputs. That means that this is going to be just two signals, A and B, and then sum and carry are the two outputs, right? And then this direction is basically your mode of that port, and say okay. So once you do that, under design sources, you will see that half header. Now I'm going to double click it, and there's some things to see. Okay, your remark starts with a double dash, and then you can say this is a VHDL code for half header. Okay, and then it's library IEEE, use IEEE dot std underscore logic underscore 1164 dot all. So this is a package name, this is a library name, and dot all says that you include everything inside the library. Now in case there is going to be, you are expecting a conflict, then you don't do dot all, you just import whatever is required, just like in any other languages, right? Okay, so now here it says entity half header is port a comma b, its mode in, and its data type is std underscore logic. So I've talked about this data type earlier also. Then sum and carry is the mode out and the same type, and notice that the last parameter doesn't have a semicolon here, it has a semicolon after the bracket. So whenever you want to add a statement, it has to have a semicolon. So this is a complete statement on its own. Now entity ends with the end entity name, then architecture name of that entity is, and then this section is known as the declaration section. Here you can declare components, here you can declare functions, here you can declare procedures, here you can declare signals, right? So we will come to what is a signal later on. Then begin, that's the body of the architecture, and end HA is the end of the body. Okay, so here this is very simple. Sum is assigned A XOR B, and the statement ends here. This is a behavioral statement. In the sensitivity list of this statement you have A and B, right? So the sequence of the statements in the body of architecture doesn't matter, and body of architecture can only have concurrent statements. It cannot have sequential statements, right? So then I can say carry is assigned A and with B. Okay, so that's the complete definition of a half adder. Here I can save it, right? Now the sequence of the statements doesn't matter because there is a sensitivity list A and B, and if there is any change on A or any change on B or both, then both expressions are evaluated, and then at the delta delay both are going to be assigned same time, sum and carry. So this is the concurrent nature of VHDL. So we are done with this, and there is nothing special about it. Now let's create a package. So I can say add sources. I'm going to add an empty file. So here I'm going to say create a file, and I'm going to call this as CKTS. So my package is called CKTS or circuits. So my file is also called circuits. I'm going to say OK. Here I'm going to add the package to the same file, same library, my CKTS, and say finish. Now here this doesn't have ports, or it doesn't have entity or architecture declaration, right? So I'm going to just cancel it and say yes. Now once I do that, it's going to say there is a non-module file because it cannot find IO, right? So this is a non-module file. So you go under libraries, go under unreferenced, and take this and drag it on top of half adder and say yes. So in hierarchy, again, if it doesn't show at the top, you just drag it up. Okay, so make sure that the package is the first thing it is going to see, and then there are going to be other files. So this basically is your my circuits library, circuits package, and this is basically your component. So here what I'm going to do is I'm going to open this file, double click it. Here it opens. Here also I need to include IEEE because whenever I do port declarations, it uses std underscore logic, and it will not know what is that. So I have to do here, I have to write library, and then library is IEEE, and then I'm going to say use IEEE dereferencing operator dot std underscore logic underscore 1164 dot all, and that's it. So now my library and package are referenced. Now I can take the half adder entity as is and make a component out of it. So here there is a component declaration. So here this has to be surrounded in a package. So I can say package, name of the package is CKTS is, and here I can say and I think it is package CKTS. Okay, sometimes, okay, this is done. Here entity, instead of entity put component, COMPONENT, and here is optional, and then end component. Okay, so now here you see I can indent this, and to show you that how the package is declared. So here if I want, I can put here package declaration. So this is how a package is declared, and it's terminated by end package CKTS, and inside this you basically declare a component, and that component declaration is nothing but the entity, but instead of calling it entity you call it component and end component. So now half adder has been added to that package. Right now if I make a full adder using half adder, I can use that. So let's go ahead and do that. So I'm going to go here and say add sources and say next, and here I'm going to create a file. I'll call this as full header. Okay, and say okay, and then make sure my library is my circuits and say finish. Here I'm going to say architecture is called FA, and here there are three inputs to a full header, A, B, C in, and then there are two outputs, which is sum and C out, right? And the mode is out, and say okay. Okay, so in naming I have done a issue with this, so let's correct that. Okay, so architecture FA. Okay, fine, doesn't matter. And here you have to say FA. So all this is done by the Vivado. It generates your entity architecture definition here. Now here I'll just add a remark: VHDL code for full header. Okay, so now here I want to use a library of my own, which is called library, and this is called my CKTS, and then I can say use my CKTS, that's the library name, dot CKTS is the package name, dot all. Okay, so now the package is included. Now that component of half header can be used here, right? So let's go ahead and use it. So before that, I wanted to tell you that I can use signals. So now what is a signal? A signal is basically a wire. It is equivalent to a wire, and that wire has to be driven. So wire has a driver. Now variable, on the other hand, is similar to signal, but it represents a memory location, and you are going to store a value in a memory location. So when you assign variables, the assignment takes immediately, but when you drive a wire, there are delays, right? So there is a difference here. The signal is driven while a variable is assigned, right? Variable is assigned immediately because there is very little delay when you put something in the memory. But when you have a wire to drive, then it depends on the driver, right? And a lot depends on the driver's strength, right? And there may be also conflicts because one wire can have multiple drivers. In that case, you have to specify which one is a stronger signal than the other, so that will take place. So we will talk about this in resolution functions later on. In case there is a wire which is driven by two or more drivers, you have to have a resolution function. So this we will discuss later on. So but I will tell you signal is equivalent to a wire. So I am declaring three wires here: S0, C0, C1. Okay, and these are of type std underscore logic, right? And that statement ends here. So I'm using three wires, and these are intermediate connections. So I'm going to take a half header, which is going to have two inputs, A and B, and then output S0 and C0. Now this S0 will also act as an input to S0 will also act as an input to half header 2, and C in as another input to half header 2, right? And wires are bidirectional, right? Unlike ports are also wires, but they have a associated mode, in out or in out, while wires are bidirectional. So we are going to use S0, C0 and C1 wires for connecting the half headers. So how do you instantiate a half header? I'm going to say HA1 is an instance of half header, right? And then I have to specify a port map. How do you do the connections, right? So there are two ways of doing this. One is called the positional, okay, the positional style, right? So in a positional style, we know that A comes first, B next, sum comes third signal as sum, and fourth signal is carry. So if I put it in that order, so I have A as an input, B as another input, S0 as the output. Okay, I have done CO let's make a change here. It is S0 and C0. Okay, S0 as the sum output, and then C0 as the carry output from the first half header, and this. So this is how you instantiate a half header, right? Another way of instantiating is if the order is not same as the order in the component declaration. So here this is called the parameter list, and here this is called the argument list. So in case you have an argument, you can do this like this also: half header port map. So port map are two words, right? And in here, let's say I want to do C0 first, right? So what will be what will it be called? It will be called, if I go here, it is called carry, right? So I can say carry of the entity. Lower entity is half header 2. Carry is assigned, okay? Carry is assigned C1. Then I can say sum of the lower entity is assigned sum of the higher entity, right? Then I can say A of the lower entity is assigned S0 of the higher entity. Then I can say B of lower entity is assigned C in of the higher entity, correct? And this. So this is called name argument. This is called positional argument. So here position has to be maintained. Here name argument, you can put it in any sequence, but then the lower entity is mapped to the signals in the higher entity using this operator. Okay, so once this is done, you have got C out, okay, which is assigned, C out is assigned C0 or with C1. Okay, so this is a complete full header using two half headers. Now in settings, okay, you can do this here also. Let me show you. In settings, I am going to simulate a full header. So general full header, so this is going to be used for synthesis. In simulation also, I will simulate a full header, right? So when I've done that, and say okay. Now one more thing, this is automatically set as a top level module. So you see this triangles, or sorry, this squares, and then the square at the top is green, which says that full header is a topmost entity. And below it there are half headers, half header 1 and 2. They are instantiated from the component half header. So I have this combination. Now I can just hit run simulation, and I am presented with a waveform window. Let me make sure I'm recording this. Okay, I am presented with a waveform window. Okay, so notice that this everything is u means it is undefined. So I'm going to say reset all. I'm going to start from here. I'm going to place for how long my input is persistent, for 100 nanosecond, and then I will see the corresponding output. So here I can right click it and say force constant. Here I'm going to force 0. Right click B, force constant 0, and C in force constant 0. So all the three inputs are 0, and then I can hit this button which says run for 100 nanosecond. So you see that inputs are 0, outputs are 0. Now these are intermediate signals, right? These are intermediate signals. I need not see them, so I can just delete them. It is not deleted, but then it is not represented on the waveform window, right? So now the next thing is I can force this constant to 1, right? And then run it again for 100 nanoseconds. Now 1 0 1 0, sum is 1, carry is 0, right? Next is I can take this one as 1 and this one as 0, right? So that is the third input option here, and just say simulate. Now here you can do view all, so you can see here over here, okay, if you place the marker, if you get 0 1 as input and carry in as 0, sum is the output. Now let's make this carry, or let's make this also force as 1. So now the sum is going to be 0, carry is going to be 1. So let me just simulate this, right? So here you see 1 1, C in is 0, sum is 0, carry is 1. Now I can make this one also go 1. So now sum will be 1 as well as carry will be 1. So once you simulate this, you can see all both the outputs are 1. So that means that my full adder is working, right? And I can close this simulation window by saying simulation waveform, right? Close simulation. So okay. So I can discard this. I don't want to save that. Okay, so that is closed. So I have a full adder using two half adders. So what did we learn here? We can make a package, right? And we can declare a component in a package. Then if we do a hierarchical design, a higher order design, which makes use of that component, I can reference to that library and package, and then from that package I can instantiate a half adder as two components, HA1 and HA2. In HA1, the assignment of parameter and arguments is by position, and here it is a named assignment, right? So basically it goes as parameter and what you want to connect to that, or a lower level entity what you want to connect to the signal at a higher level entity. So carry is connected to C1, sum is connected to sum, A is connected to S0, B is connected to Cin, right? And so this is my full adder. Now can I have another architecture over here? Why not? Nothing stops me. I can say architecture, okay, FA2 of full adder, that's the name of the entity, is, and then you see and say end of FA2. Okay, ARCHI. Okay, so I have, okay, so I have forgotten begin, right? So that's why it's complaining. Okay, so I have created another architecture for the same entity, but this time I'm calling it FA2, right? So here I can define it this like this way. Sum is assigned A XOR with B XOR with C, and carry or C out is assigned something or with something or with something, correct? And here I can say A and with B, B and with C, C in, sorry, and C in and with A, and then semicolon. C in. Okay, so now there are two architectures. One is basically a structural style. The other one is going to be data flow style, which we have discussed earlier. But then let's look at message. Message says there are, so on attempting to, so there are two copies of an architecture. So that's what it is going to give a warning. So let's remove this error. Okay. Okay, so now the question comes is, which one is it going to use and what will it look like? So first of all, I'm going to comment this one, right? I am going to comment this one, right? Okay, okay. So first I'm going to commit the second architecture. I'm going to save it. And here I am going to go to RTL and say open elaborated design. Say OK. So this is elaborating the first architecture because the second one is commented out. Sorry about that. Let it finish elaboration. Okay, of course, you didn't have a synthesis done and you didn't have the IO constraints assigned. So what is it showing? It is showing a half header 1, half header 2, and then it is showing a OR for the cout. So this is what I was talking about. This wire is called S0. So it points here, you see here, it points here at S0, while this one is C0, right? So this one should be called C0. Why isn't that there? And this one should be C1. But why is it not calling C0? Anyways, and this one is the output. And if you double click this, you are going to see a half header. This is going to be XOR as sum and carry as this. So if I press a negative, so that's the symbol for this, right? So let's go up in hierarchy. Okay, so this is how it is elaborated. So I'm going to close that elaboration, close elaborated design. So this is using two half headers. Now I am going to comment out this one. Okay, so now I'm going to uncomment this one. Okay, so now this is, I'm going to save it. So I have a different architecture here. So let's say what it results to. If I say open elaborated design, say OK. Now it is elaborating a new design because this is declared differently, right? Okay, so now you see you have got A XORed with B XORed with Cn to give sum. And then you have got A and B, A and Cn, and then I have got B and Cn, right? A and Cn and B and Cn. And then you are going to OR them using two. So each one is ORed with the other one, right? So each one is ORed with the other one, right? So this is another, you know, functionality defined in a different way, right? Now the question is which one is going to be faster. So I bet that this one is going to be faster than the other elaboration. So we will learn this later on. Okay, so I'm going to close the elaborated design. So I just wanted to show you that it depends on you how this would be created. And in case you do not specify it, as in case of behavioral style of architecture, then it is left to the tool to optimize it. If you do a structural, it will do as you tell it, but or a data flow, it will do as you tell it. But if you do behavioral, it will do as it wants to do, and then it will optimize it. So is that a good thing? I think it's not a good thing, right? So mostly I'll try to design either a data flow or a structural close to the design rather than leaving it behavioral, and you will see this later on when we do a barrel shifter. Okay, so having said that, I can take this entity and enter it into a package, which is the same package here. Control V, and instead of entity I will call this as component, and is optional, and end component. Okay, so I will do a indentation and done. So now I have full adder also declared inside the package, right? So I can cancel all this. So I have a package which has half adder declared, full adder declared. Now let's say if I want to do a AND bit adder, so I can go here. Now this is something which I want to talk to you about. Okay, this is called generic. So what it means is I am going to tell when I instantiate what should be the width of my component or what should be the word size. So in that case I'm going to declare the size or the width as generic, and then I'm going to pass an integer when I instantiate a component, right? So this is how you use generic. So I'm going to show you how to use generic and how to pass the width of the design or the word size using generic, how to pass that to component at the time of instantiation, right? So let's do this. Okay, coming back to Vivado, I am going to create another design, add sources, create a design, and I'm going to say adder n bit. Okay, so this is called adder n bit. So the name says what it's going to do, and the library is called my circuits, and say finish. And then architecture I'm going to call A and B, adder n bit, and this is going to have instead of scalars like std underscore logic, it is going to have vectors. So this is a vector, is a composite type, it is an array, right? It is the only inbuilt vector you will find in VHDL, or you have to create your own, right? So let's see what this is. So I can have A comma B, and this is going to be a bus or a bunch of wires. Let's say the default value is 8 bits, so 7 down to 0. Then I am going to have C in as a scalar, so I can put here C in, and that C in is a scalar. So what do you mean by scalar? There's only one wire, right? Then I am going to put here sum. Sum is going to be a vector again, because for n bit inputs A and B, n bit output sum, that's also going to be the same width as the inputs, right? 7 down to 0. And then you are going to have C out, right? So this C out is a scalar output, so this is also output, this is also output. Okay, so we have got three scalars as input, three vectors as inputs and outputs, and two scalars as input and output, right? And say okay. So once you do that, you are going to have a full adder and n bit adder here, adder n bit. So double click that, and I am going to put here a simple remark that this is a VHDL code for n bit adder, correct? And here I am going to instantiate a full adder, so I have to include the include file. So I can say library my circuits, and from that library I'm going to use a package from my circuits library, which is called circuits, and then I'm going to say all, instantiate all, and say okay. So this is my referencing. Now I want to create a ripple ladder. So what's a ripple ladder? The carry of one full adder is going to act as a carry in for the other full adder. So carry out of one adder will be rippling to the carry in of the next adder. So for an n bit, there is going to be n adders, and all these n adders are cascaded. All these n adders are cascaded, right? So let's see, I need a intermediate. Okay, so I need a intermediate signal which accounts for all the carries. So I'm going to add a signal, and that signal I'm going to call C, and this is going to be std underscore logic underscore vector. Just as over here, this is 7 down to 0. This is going to be 8 down to 0 because you need one extra carry in, right? So let's introduce generic here. So to introduce generic, you will say generic and then open the bracket and say I'm going to use n as generic, and it is of type integer, right? And then you have to give it a default value, because without a default value, if you try to run it, then it will be confused. What is the default value of n? So I'm going to give it a 8. And notice that this is going to be n minus 1. And this is going to be n minus 1. Correct? And similarly, this vector is going to be n down to 0. Now, I can go on and on talking about what is n minus 1 down to 0. Down to is a one word. And this is a vector which is saying index it from 7 to 0. Index it from 7 to 0. It's an array. Or you can say 0 to 7. Then you have to say 0 to n minus 1. So that will be going, the indexing will be going from 0 to n minus 1. So if you use 2, it will be indexing from left to right. Now if you go down 2, you will be still doing indexing from higher number to a lower number. Now this can also be used for connecting to buses and have a flipping the entire word. Okay, so I can have two buses which are defined, one as n minus 1 down to 0, other one is 0 to n minus 1, and when I connect them, this flipping would be automatic. So basically for flipping, you do not have to do anything but just connect it differently, right? So I'm not going to go into details of all that. Many books basically spend a lot of time doing that kind of stuff, right? So it is counterproductive. So let's go ahead and do this. Now I know that C0 would be assigned C in, right? And after that, I need to start instantiating. So I will say loop 1. So this is the named loop, and this is a for loop. For I in range 0 to n minus 1. Generate. So generate is going to instantiate. So why do I need a for and generate? Because n is a variable, right? So how many times do I have to loop? N times. I have to instantiate n times. If I know this n time prior, like for example, if I know it is going to be 8 and 8 only, not a variable 8, then variable number, it is going to be just 8, then I could have written FA1, FA2, FA3, FA4, FA5, FA6 up to FA8, right? But here n is a variable, that's why I'm using a for loop, and it's going to loop n times, right? And each time it loops, it's going to instantiate. So I'm going to say FA1 instantiate for full adder, okay, with the port map, which as follows: AI bit is added with BI bit, gives, okay, so this is by what you call position, and has a carry in of CI bit. AI, BI, CI. And then so that for the first turnaround I equal to 0. So A0, B0, C0. Then it's going to be sum 0, right? Sum I. And then it is going to be Ci plus 1. So this is going to be a carry in for the next bit, correct? And that's it. So when it goes to n minus 1, then this would be C n minus 1 plus 1, or Cn. That's why, this is going to be 1 bit more than the inputs. So inputs are 8 bit while C is 9 bit, right? So to account for 1 extra C0, right? That's why it is there. Then you do this and you can say end generate loop 1. Now you can also nest the loops. As we will see when we do multiplier, you might nest 2 for loops to instantiate. Okay, so that's like a array. So once I have done with this, the C last C out is Cn. That is coming out as C out. Okay, so that would be Cn. Okay, so now you see how concise this is, right? You have instantiated a full adder which is n bit wide, and n is a variable, right? So let's see how to instantiate it. So now you see here, still LP1 is a top level module, which I don't want. I want to right click this and say set as top module. So that's going to shift over here. So now this is a top module, and FA sits inside that. Now if I go to general settings, I can go here. I'm going to say adder n bit in simulation, and also for synthesis adder n bit. Okay, and say OK. Now if I run the simulation, by the way, these errors and warnings are from the previous one, so I can clear them. So let me just finish it and I'll clear them. Okay, sorry about that. Okay, so now the messages, come on. Now the messages are there, some warnings are there. Parsing on the fly. Don't worry about that warning. There are no errors, right? Okay, so again, you see C is a 8 down to 0. So this is going to be 9 bit. But I don't want to look at C. So I'm going to just delete this. N is 8, which is by default. So I don't want to see that either. Okay, so now I'm going to reset this. Now I can right click it and say force a constant. I want to add 2a, that's hex number, force a constant 3c, and carry in is 0, force a constant 0. Okay, so I'm adding 2a to 3c with c in as 0, and if I simulate this for 100 nanoseconds, I can see over here. So 2a plus 3c is 6 and c out is 0. So let's check this. So I'm going to go to calculator, and I'm going to go to a programming calculator and put this as hex. So I want to add 2a plus 3c. So that's going to be 6. So that's 6, and c out is 0. Right, now if I introduce c in as 1, then it is going to be 6. Right, so if I run this again, this is 6. Now let's add a number, ff. So let's see what happens. So here I'm going to enter the highest number as ff, and here the highest number is ff. Okay, so I am going to add ff to ff with the carry of 1. Okay, so if I run this, I have ff and cout is 1. So let's check this on the calculator. So I want to add ff plus ff plus 1. So the answer is carry is 1 and the result is ff. So the result sum is ff and cout is 1, right? So this is working, right? So this is a full adder which is working. So what did we learn here? We learned how to use generic and how to use generate, how to use generic to pass this information. Now you would say that it is going with a default value of 8 only, but I haven't instantiated it, right? I haven't instantiated. So let's say if I want to make a 16-bit adder, so first of all I would have to go here and make a component out of it. So I will go to circuits. I'm going to say entity, I'm going to say component, and is optional, and I'm going to say end component, correct? And let's indent this. Okay, so this indent this also. So this is my n bit adder. So let's say I want to make a 16-bit adder. So I'm going to say create a new design and say create a file. I'm going to say adder 16-bit, right? So I'm telling you how to do a generic design. Then the library is my circuits and say finish. And here I am going to say a comma b is going to be 15 down to 0. Okay. Then I'm going to have c in as a scalar. Then I'm going to have sum as out, and this is also going to be 15 down to 0. And then I'm going to have c out, which is going to be a scalar output. Okay, and I'm going to say okay. So adder 16-bit I can declare as a top level module, though right now there is nothing in it. Okay, and I'm going to double click this one, and here I am going to remove this and say VHDL code for 16-bit adder. Okay, and I am going to use library my circuits, and I'm going to use my circuits dot all, correct? So I have instantiated it. Okay, so now I want to make use of the component which is going to be that. So here I can say A16B, okay, is a adder n bit. Okay, so that's the name of the component, right? So you say adder n bit. Okay, then I would say generic map, and here I am going to put here 16, correct? And then I'm going to say port map, and here, so this is 16-bit wide, so I can here given, so what are the inputs here? A, B, C in sum and C out, right? So I can give here A comma B comma C in comma sum, right? 16-bit wide comma C out. Okay, so this is done. So now this is a 16-bit adder, right? Now I have used generic to pass this information 16, which was by default 8. Now it has become 16. Now the generate will loop will run 16 times rather than 8 times, right? And then similarly cin would be 17-bit wide, and AB are 16-bit wide, sum is 16-bit wide. So you understand what is the use of generic. Okay, so let's see. This is a top level module, right? Let's see if I can make use of that. So here under simulation, I'm going to use 16-bit, and general also is going to be 16-bit, right? Okay, and say okay. Now I can just run simulate. So you see how simple is it to use generic to pass on information. Now it's just not the width of the word. You can also pass in information like delay. So there is something called standard delay format file or SDF file, which is also there in Verilog. Something similar concept is there in VHDL also. And you can map the delays to various gates in the circuit, right? So now you see automatically everything is 16-bit wide, right? So what I'm going to do here, okay, so what I'm going to do here is I'm going to reset this, and I am interested in, okay, so you don't see any intermediate here because there are no intermediates that inside the lower level hierarchy. So here I'm going to say force constant, and I'm going to say 2A 3C, okay, and then B input I'm going to force a constant C4 D2, right, and I'm going to force a constant Cn is equal to 0, right, and I'm going to run it for 100 nanoseconds. So the answer is EF0E. So let's check this. So I can go to calculator and I can go to hex, and I can say I want to add 2A 3C plus C4 D2 is equal to EF0E. EF0E, and C out is 0. So this adder is now 16-bit. So now you can see that you can write components which are scalable. Like we will write an entire ALU, arithmetical logical unit, just like this, so that we can easily modify the design to be 32-bit or 64-bit, right? So that's a good practice to do. So I'm going to close the simulation window here. Okay. So I've shown you how to use generic and generate. Let's see how much time it has gone in. So I have taken your 58 minutes. So I'm going to conclude here. Remaining part of the combinational circuits I am going to add in the next session. Thanks a lot.